minimize. Actually, we should change that into maximize. Okay, no, we minimize. Let me see, minimize, maximize, minimize. Okay, we do the minimize x1 plus x2 plus x3. And the side boundary is x1 is a continuous and between minus 5.12 and 5.11. And x2 is integer between 0 and 15. x3 is a discrete and can be selected from these A numbers. So please arrange a proper binary representation scheme to match the variables values of each of the three inner variables to binary string in the genetic algorithms. So first, we want to do that, and using a whiteboard. If you already download the PowerPoint, so you can check it out on the site. Okay, we have a whiteboard here. We have x1 between minus 5.11 to 5.12. I was wrong. This is 1, 2, this is 1, 1. And x2 will be between 0 and 15. x2 will be 0 to 15, integer. So integer means the step size is equal 1, right? And this is a real number. We have to determine the step size. Step size, we make it 0.01, 0.01. And x3 is a discrete. They only have A numbers to select. Okay, so there are no step size, only 8. So since only 8 possible number you can select, so binary string will be exactly equal 3, right? N equal 3. So we need a 3-bit. 3-bit will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1. So binary value, decimal value is 0 to 7, matching to 8 different possible values. So based on the decimal value, and we will know that, for example, that if your decimal value is, remember that, let's do that later. For this integer, from 0 to 15, so it would be like upper bound minus lower bound divided by precision is 1 plus 1, 16. So it's called a 4-bit, okay? So we need a 4-bit, 0, 0, 0, 0, 0, 0, 0, 1, all the way 1, 1, 1, 1. Okay. 1, 1, 1, 1 is a decimal value is a 15. This one is 0. So we need a 4-bit to represent the x2, the integer variable from 0 to 15. So this is exactly the same. decimal value from 0 to 15. Okay. And for this continuous number, we need the upper bound is 5.11 minus 5.12 divided by precision 0.01 plus 1, 1024. So we need a 10-bit. So first you have to understand that before that, when we, in our old traditional optimization problem, we all assume the design variables are continuous, right? But later on, we said that when the design variable are not continuous, but they are integer or discrete, then we have big trouble. Then we have to run branch and bound method. So we might need to run up to 2 to the n plus 1, right? So many different optimizations just because we have n design variables which are not continuous. But here you can see that for x1 is a continuous variable from -5 to 5, and we're using the precision 0.01. Actually, 0.01 is not very high precision. But still, because of this one, they need more than 1,000 representations, so they take a 10-bit. So x1 take 10-bit. But x2 is integer, only take 4-bit. x3 is a discrete number, so only take 3-bit. So for the total 17-bit, there are a lot of percentage used to run x1. So you will see that for genetic algorithms, if the design variables are integer or discrete, actually they are much easy to be handled because less binary string, less total number of representations means that they are easy, the best substring can be found. So actually, those are relatively easy. But for X1 is more trouble. So you see that in original traditional optimization problems, integer or discrete, those are non-continuous design variables are very difficult to be handled. But now actually piece of cake. Okay, that's important information. Okay, now we need to define a scheme like that one to handle our optimization problems. And then, okay, then based on your binary representation scheme, please define 2 binary strings to represent 2 specific design. Okay, now we are going to work on a real design. We have x1, 0, 0, 2, 0, 0, and 2. x2 is 1.23, 7, and 11. Okay, then we have to go back to mapping things. Okay. We start from the last is a discrete values 2. And if you see the PowerPoint, then you see that for x3, the a possible discrete numbers is 1, 2, 4, 6, 8, 11, 13, and 34. So 2 is the second one, right? 2 is the second one. 6 is the second one, means the first one here, second one, third one, fourth one, fifth one, sixth one, seventh one, eighth one. So we only need to know that which binary decimal number, because decimal number will be 0 means the first one, 1 means the second one, 2 will be third one, this will be fourth one, because final one will be 7. So right now, we need to represent this the discrete value too. So it means the decimal value should be 1. So that will be 0, 0, 1. Okay, 0, 0, 1 for this one. And design variable 0 is integer. Okay, from 0 to 15. Because it's the first one. Because 0 all the way to 15, and this all the way to 15 too. Because 0 decimal value is 0. We have 4-bit. The decimal value starting from 0 to 15. And so since the integer is 0, the 0 is the first one, right? First one is a decimal value always 0. So it's a 0, 0, 0. This will be 0, 0, 0, 3-bit. No, 4-bit. 0, 0, 0, 0. 4-bit is a decimal value is 0, means the first number. First number is 0. So this one. And then this 0. This 0, we have to know that is how far from the left side. I need to clean it again. Because we start from minus 5.12. Then we're at 0.01, right? Every step size we add it like that one. First one, then 1, and 1, and 1, 1. And right now, if this 0 means that we start from the lower bounds of 5.12, then we need to add how many step size? Every step size 0.01, right? To be 0. Right now, we try to represent a real number as 0. And so we need how many step size? This is minus 5.12. So we will need 512 step size to make a summation into 0. So since the step size 512, step size means this is a decimal value. Because the decimal value first one will be 0, right? All the way to 1023. The first one represents the smallest minus 5.12. The decimal value 1023 will create the final value here. So we have 10 binary string. Find out is a decimal value. Then the decimal value means the step size. Start from smallest one. Okay. So if we need 512 steps to move from 5 minus 5.12 becomes 0. So the step size 512, also the decimal value. Okay, then you need to find out what are the 10 binary string. It's a decimal value is 512. I don't know how to do that. But you have to find it. I don't know. Find a 10 digit. It's a best decimal number is a 512. Okay. So together with earlier, we have 0, 0, 0, 0 for x2 be 0. And also we have 0, 0, 1. Decimal value is 1. And it's a second discrete number 2. Okay, so we have that one. Any question on this before we go through the second one, second design? Now, are you okay? Now he's not here.
Okay, Professor.
So you're okay. Others? Let me check it out. How about Sanabria. Ortega Sanabria. Are you okay? Christian Martin Ortega Sanabria. Are you here? Oh, not here. Only name here. Matsuka. Morignas Matsuka. Are you okay? Strange. Fendi, are you okay?
Yes, I'm good, Professor.
Okay. And then we go into the second problems. Let me find a whiteboard. Wait, I couldn't find a whiteboard. Every time I couldn't find my whiteboard. Where's whiteboard? Wait a second. Okay, I find a whiteboard. Okay, now we run the second is x is 1.23, x1 is 1.23, and second is 7, then it's 11. Okay. Yeah. Okay, we start from 11. 11, you check out the possible discrete numbers, 1, 2, 4, 6, 8, 11. So that's 6. Okay, so this is 6 member in the list. 6 member in list. So first member, 2, 3, 4, 5, 6. You are here. So for binary representation, 0 should represent the first one, right? This should be, decimal value should be 1. So your decimal value should be 5. So for the 3-bit, that would be 101. So this is 4, this is 1, right? So this represents this discrete value 11. And 7 from 0 to 15. You are the ace because 0 is the first one. 7 will be ace. But the decimal value is 7. So decimal value 7 will be 0, 1, 1, 1. Because this will be 4, this will be 2, this is 1. So 0, 1, 1, 1 represent this one. And 1.23, we have to find out how many step size from the right. So minus 5.12 plus how many step size? Step size 0.01 equal 1.23. So that's 1.23 plus 5.12 divided by this one. That'll be 635. This 6.35 divided by point of this one. So since step size this one, so it will be equal to its decimal value. So we need to find out a 10 number binary string is a decimal value is a 635. Okay, so you have that one. Then adding this, and then after that, then you have that many 17-bit binary string. This looks very small. This is bigger. Okay. Okay. Then we come back here. We have an unconstrained optimization problem. Try to minimize x1 plus x3. Okay, so earlier we just based on the binary representation scheme, we will find out two binary strings to represent these two designs. Okay, and after you have that 17-bit two binary string, we ask you to perform crossover on these two strings by exchanging bit between A and 12. After you do create two new binary strings, then you have to decode them again to find what are the new x1 and x2 and x3. Okay, some might be changed, some might not. And then you need to find out the x1 and x2, this x1 and x2, right? Because you have new children. This is a parent. After crossover, you have the children, and you have to find out they are finished there. But let me explain finished. I need using a whiteboard. The finish function. Okay, finish function. Is not this function. This function in automation we call it object function. This f is called finish function. Okay, in GA we try to maximize the finish function. Try to maximize that. So the higher the better. But in automation we try to minimize that. Right? So we have to find out somewhere to change the minimization problem into a maximization problem. But before we change to maximization problem, we need to minimize that because in a penalty, because the next one we will discuss the constraint function. If we have a constraint function and we said that, and in genetic algorithm, we only using one measurement, just called a finish function. We cannot using constraint function. So we have to combine the constraint function into a part of the object function. So we're using penalty function approach to change the constraint violation with the function to be minimized together into a called a pseudo object function. Okay, that's
Sorry,
yeah.
sorry, Professor. You are not representing the ball on the screen.
Okay. Okay, thank you. Genetic algorithm based on finish function, and usually optimization will try to minimize that. So this small f is to be minimized. But because when we have a constraint function, we need to add the object function plus some penalty, right? Some penalty function, and to become a pseudo object function. Similarly, to be minimized. So when we have the minimization problem, or we have a constraint optimization problem, then we have a pseudo object function. They are all to be minimized, right? But in genetic algorithm, we try to maximize. So how we can convert the minimization into maximization? There are two approaches. One is we're using 1 over object function or pseudo object function, because we want to minimize that. When this denominator is smaller, then this 1 over smaller number will become bigger. Okay, this is one approach, 1 over a function to be minimized. But in reality, is a better way to do is we're using a big number. This is called a maximum number. And to subtract this number or this number. For example, that we have 10 designs, and their object function is 3, 5, 10, 12, 20, 50, and maybe 60, 70, 80, 90, 1, 2, 3, 4, 5, 6, 7, 8, 9, 100. For example, we have 10 designs, and these are their object function values. Smaller the better, right? So 3 is the best. 100 is not as good. So we need to find out a value to subtract them. If we select these as the 10,000, then this one, we need to, the new finish, it's called a finish function, will be M maximum minus your object function. So this 3 will become 9997. This will be 9995. Likewise, this one will be 900. So for finished, the larger the better. Yeah, this is the best, right? This is the worst. But are these okay? Howard, what do you think about this one?
Yeah, it's okay.
It's okay. It's okay means the 3 is the best, still the best, right? 100 worst, still the worst, right?
Yes.
But how about that? We have 10 people to run 100 meters, right? One run 3 seconds, and second one run 5 seconds, and the last one run 100 seconds. And after this conversion, 3 of course the best. After the conversion, this one run 3 seconds in 100 meter. He's finished 9,997. This one, even you crawl, you take 100 seconds to 100 meter, they still have 9,900. What do you think? There's something wrong here. None. What do you think? What is the problem here?
1000 minus 3 in 997, right?
And tell me what is the problem here? What's the problem here? Because Power says it's okay. Assuming that the most important procedure in genetic algorithm is selection. Selection is that we form a rotor wheel, right? Let every design a share of area If you are better, you have bigger shape, bigger area, right? But if we using this kind of scheme, 9997, 999, everyone should be similarly, right? Not much different. This one is 3. This one is 100. In here, this so outstanding, right? But after you convert here, this is 9999, 9997. This is 9996. In terms of this divided by the total, this, they are almost identical. So if we choosing 10,000 to do this conversion, we lost the comparison at all because they are actually the same, right? So we shouldn't using that big number. How about we select 100? If we select 100 here, a totally different story. 100, this one will be 97, right? First one 97, this one 95, and this one 90, and this one 80, and then 50, and 40, and 30, 20, and 10. Final one, 0. Summation of all of them is how much? 237, 400. Maybe like a 520. In this new scheme, 100 will be like 20%, right? So 1 will be like 20%. This one with no area. This one only have maybe about 3%. So it fairly represents the importance of different area. So this maximum number, usually we select for that generation. For that generation, if the largest is 100, we are using this one to select the F maximum. Either just using this one or 1.5 of this one, so that the scaling will be normal distribution. Otherwise, you cannot pick a fixed number, because if you pick 100, then how about this is 500, this 1,000, then you have a problem. So this should be adaptively based on the largest this object function, and select this one to do the subtraction. Okay, this is the way. So we need to do that, but because we are not going to run genetic algorithm in entire procedure, so we don't do that, but you need to know that one. Okay. Okay, go back to our problem statement. After you have done that, then we run the constraint optimization problem. The difference to this one is that we add the constraint, 2 constraints. Otherwise, they are the same. 2 constraints. So you have to convert the constraint into penalty function to be added on this object function to be minimized. So your pseudo object function will be this object function plus penalty function of these if they are violated, and the penalty function if this is violated. Still, the summation of all of them is a function to be minimized. So if you run the real finish function, you need to change it into a function to be maximized. Okay, so you need to find a number bigger than at least this pseudo object function and do the subtraction. That one could be a good finish function. Okay. So based on your definition of finish function, and because you need to determine what are the penalty function, and also how to convert the minimum to be minimum, the pseudo object function to be the finish function. So you need to define the scheme. After you define the scheme, then if I give you 2 designs, then you need to find out the finish function of these 2. then you have to check whether or not they are violating any constraint. And then if yes, calculate the penalty. If no, calculate the object function. If yes, calculate pseudo object function. Then based on finish, what should be their finish function? Okay, that's the second part of this homework. Any question? Any questions? Because these are likely will appear in the final exam. So please ask your question. Do you have any question?
Sorry, what is
Yeah.
the method that you utilize to do the pseudo function? The sum that we learned, that's the method we need to use to
What
to
function? You say again.
the function, because in this case we have a constraint optimization problem, right?
Yeah.
And we need to use summed
Penalty
SUMT,
function.
yes, to to do how do you
No,
say
no. Let me find the penalty function.
a pseudo objective function, right?
Not several object function. That's totally different stories. Oh, don't
No,
match
no,
that.
pseudo objective
Pseudo.
function.
Okay, I will show
That's
you. Let me bring up the code. Constraint. Wait a minute. Sequential unconstrained minimization. SUMT. Wait a second. I need to find out the SUMT, where are they? SUMT. Okay, I found it. Okay, I will share this one. This is the sequential unconstrained minimization techniques. So it will convert an unconstrained, it will convert an constrained optimization problem into unconstrained optimization problems. And since genetic algorithms, we cannot handle constraints. We can only handle a finish function. So we definitely have to using some approach to convert a constraint optimization into an unconstrained optimization. And this is what we are going to do, okay? So we are using exterior penalty function. So exterior penalty function is like that, okay? The fx here is the object function to be minimized. In our earlier example would be a function equal x1 plus x2 plus x3, right? And then the second part will be a penalty if there are violations. So since we have only two constraint functions, so this Q will be, no, this J could be only two. We have G1 and G2, right? And for each G1 and G2, we depend on whether or not there are violations. If we plug x1, x2, x3 into the G1 and it's more than 0, then this will be 0, okay? So no penalty. But if G1 or G2 we plug in the design variable x1, x3, it becomes positive, like a 1. So 1 and 0, of course, 1 will be the content to be penalized. So we have a 1 here. And then depends on what is it post exponential here. If we q equal 2, then if 1, then square 2, still 1. If this is 2, then square 2 will be 4, right? Then depends on this parameter. So if parameter we start from 1, then it will be 1 times this. So you just let me know that your finished function scheme. You will say that, okay, our rk equal 1, q equal 2, then everything will be fixed. So we go back to our using a whiteboard. Okay, based on what I said, if we object function earlier is x1 plus x2 plus x3. Then you need to define your finished function equal to a large number. We define this later, but it should be a large number minus this one or this one, right? If original is unconstrained optimization problem, then you just put it here. But because we have a G1 and G2 now, we have G1 and G2. So we were using pseudo object function. And pseudo object function actually is F plus RP. And actually it's a G1 square plus G2 square. Then you have to say if G1 greater 0 or G2 greater than 0. Because in our formula, if G1 smaller than 0 or equals 0, G2 small, then you don't have that one. Only when they are more than 0. Okay. If they are more than 0, then you have penalty. You select 2. You can select that one. Then you also can select this one is 1 or 10. You just define them. Okay. Once you define this number and this number, then and also this number, then if I give you a design of x1, x2, x3, then actually you will calculate this one. You also can calculate this one, and based on 10 and this one, then you have a pseudo object function. And based on this one, if this is higher than this one, more than this one, then you have finished function. Okay? I will go home to make a more specific definition of that one so that you don't have to choose by yourself. Choose those parameters for you so it's easier for you to follow. Okay? Any question?
And sorry, Professor, another question is,
Okay.
when is the trust design analysis homework going to be, when we need to give you the homework?
When you will submit the homework, I will define them. I will go back. Tonight, I will think about it, and I'll give you a time, okay?
Okay, thank you.
But the trust optimization problem last week, I already told you you should work on that, and I hope you can finish that next week. Because optimization tool is there in MATLAB and analysis code I already provided. All you have to do is write some object function and constraint function and also linking to those are pre-10 bar and the re-10 bar things. So it will take you maybe 1 or 2 days to do, but you should work on that one, okay? Because that is the first very practical engineering optimization problems in our course. So we need to learn how to do that. About the time, I think it's okay. I will give you plenty of time to submit. You know that all I wish you to learn, to know. So even you late submission, I still give you score, right? But so due date is not that important, but you should work on that. I will double check again the submission date and later. Okay, any question? Any? Okay, if no, then I want to stop here today. We'll take a 5 minutes earlier to stop this class. Okay, thank you. Bye-bye.
Thank you,
Thank you, Professor. Bye.
Professor.
Thank you, Professor.